All right, we are going to talk about one more geometric method for measuring gerrymanders. How do you measure geometrically how weird the shape is? That's what we've been talking about last time. Last time we did the convex hull ratio, and this time we're going to do another way of measuring the weirdness. These two things, they give you different answers because they measure the weirdness in slightly different ways. Here's the idea though. Just like last time, if we have, say, a shape like this is not so weird. A shape like this is super weird. What's the difference between this shape and this shape? You know, last time we talked about the difference in terms of the convex hulls. This time around, we're going to talk about the difference in terms of the perimeters. These two shapes, I would say they have roughly the same area. I'm actually not sure exactly that the areas are the same, but they look about the same. That is, you know, you could, if you wanted to paint the inside of this figure, it might be about the same amount of paint as the inside of this figure. But the perimeters, I would say, are very different. This one has a much longer perimeter. Perimeter, remember, is the distance around the edge, all right? Whereas this one has a shorter perimeter than that one, all right? And that's what this last method is going to measure. So I'm going to say just the general idea behind this. The basic idea is that weird shapes tend to have a big perimeter. With respect to their area. Right? You can have a weird shape is, according to this idea, a weird shape is one where the area is not so big, but the perimeter is very big. That would indicate that the shape is super wiggly, right? Those wiggles, every one of those wiggles gives it extra perimeter without really giving it much extra area. So the name for this thing that is going to measure wiggliness in terms of perimeters versus areas, it's called here's the big word, Isoperimetric Quotient. And you can see the word perimeter in there, Isoperimetric Quotient. It is defined as a fraction, which is the relationship between the perimeter and the area. So I'm going to say this, the idea is to make this fraction area divided by perimeter. And so this thing, if the perimeter is super big compared to the area, then this will be close to 0, which is regarded as bad. Close to 0 indicates a weird shape, just like the convex hull ratio. Close to 0 is weird. Close to 1 is normal. So if the perimeter is much bigger than the area, then this will be close to 0, which indicates a bad shape. And if the perimeter is more or less in line with the area, this will be greater than 0. Okay, this is a very basic idea. Actually, this needs to be modified as far as formulas goes. Actually, this formula is not a sensible formula geometrically, and I'll tell you why. So what's wrong with just doing area divided by perimeter? I mean, this more or less is what we want to measure. It's the ratio of the area to the perimeter. What's wrong with that is, I'll just show you by an example. This area divided by perimeter, if you just do that fraction, this depends on the scale of the picture, not just its shape. And this is a bad thing. You know, if our measurement is supposed to just measure how wiggly it is, then it should not depend on how big the thing is, or the scale at which we measure it. Another way to think about this is in terms of the units that we measure. This depends on the scale, meaning if you were to change units, say from measuring in inches to measuring in feet or centimeters to meters, it turns out actually this value would change. The A divided by the P, it depends on the scale. not just the shape. We want this thing to only depend on the shape. Here's what I mean by depends on the scale. See if you agree with me. What if I consider the unit square? This is a square of length 1 on each side. What would this quotient be if I did this for the unit square? Well, in this case, the area of the square. Do you remember how to find the area of a square? You know, areas can be tricky, but I'm sure you learn at some point the area of a square or even a rectangle. It's the length times the width, which in this case would be 1 times 1, which is 1. All right. And what about the perimeter? The perimeter can also be tricky for a weird shape, but this is not a weird shape. The perimeter, we can just sort of go around. It's 1 on each side, and we add those all up. It's 1 plus 1 plus 1 plus 1, which is 4. All right, and so this fraction, a divided by p, is 1/4, right? Okay, what if, I said this, it turns out this depends on the scale. What if we measured the same shape, but let's say we used meters here, but I'm going to use centimeters here, right? So this is 1 meter, but if I measure in centimeters, this would be 100 centimeters. This one would be 100. I would like these two quotients to be the same answer both times because it's the same shape. I changed the scale, but it doesn't matter. What I want to be measuring is how wiggly it is, not how big it is. Anyway, what do you get here? In this case, the area will be 100 times 100. Here it was 1 times 1. Here's 100 times 100, which is 10,000. And the perimeter, we go around and add up 100 plus 100 plus 100 plus 100. That's 400, right? And so now this quotient, a divided by p, is now 10,000 divided by 400. And actually, I can simplify the fraction. Just cross off some zeros. This is 100 divided by 4, which is 25. Actually, this is totally different from that, right? This is less than 1, 1/4. This is far greater than 1. This is 25, right? The moral of the story is this fraction here, a divided by p, is not a meaningful measurement of the wiggliness of the shape because it depends a lot on the scale, not just on the shape of it, but it depends on the scale. In other words, it depends on the units with which you measure the shape. Really, the problem from an abstract point of view, and maybe you could have this idea, it doesn't really make sense to compare. Can you hear them yelling up there? It's all in good fun. It doesn't make sense to compare in a fraction the area divided by the perimeter. If you just think about the units in which these things are measured, area is measured in like square whatever, square meters, square feet, whatever, square miles, while the perimeter is not a square distance, it's just a straight up linear distance, right? Feet, meters, whatever. So here what you have is you're making a fraction with two numbers which have two different kind of dimensions. The area is a two-dimensional thing. The perimeter is a one-dimensional thing. And it should not surprise you that that doesn't actually give you a meaningful thing when you make that division. Because you want, if you're going to make a ratio of things, you want them to actually be the same type of thing that you're comparing one with the other. So actually, I said this formula needs to be adjusted, and it's very simple. It turns out all of this business about the scale just goes away immediately. All you've got to do, I will tell you, instead, use this formula, a divided by p squared. It turns out if you square the denominator, then this and this now are both kind of two-dimensional things. They have a similar nature to each other, and so actually now it does make sense to compare these two things in a fraction. And if you look back at the square again, you'll see, in this case, right, here, the area over perimeter squared, this would be 1 over 4 squared, which is 1 over 16, right? What about when it's 100 on all sides? Here it would be area divided by perimeter squared, which is now 10,000, like it was before, divided by 400 squared. And it turns out if you just multiply this out, you get 1 over 16 again. Actually, this does measure some kind of property of the shape, and it does not have any regard for the scaling. So this is a better formula. It turns out we're going to modify this slightly, ever so much. This would work fine if you use it in the real world, but when people actually use this in the real world, they change the formula just a little bit. The true formula that people use, so this is called the isoparametric quotient, or the isoparametric ratio. Sorry, quotient. I mean, it's a ratio. You could call it either, but I'm going to call it isoperimetric quotient. And this is the real formula. I'm not going to change it anymore. I'm going to write IQ is 4 pi a divided by p squared. All right. This formula, unfortunately, you're going to have to memorize this. I know I said like in the first day of class that you're not going to have to memorize any formulas. I guess it wasn't quite true. This, I will expect you to memorize this formula. It's not so complicated, right? It's 4 pi a divided by p squared, where a means the area, p means the perimeter. Why they got to put the 4 pi in there? Why do they got to complicate things? This would have worked fine. The only difference is, you know, whatever this number is like that same number times something like 12, because pi is close to 3. Why do they do it this way? The 4 pi, I don't know if you care, but the 4 pi makes it so a circle has isoperimetric quotient equal to 1. The 4 pi is just put in there as a convention so that you get 1 for a circle. And this isoperimetric quotient of 1 is the maximum possible. So 1 is the greatest possible isoperimetric quotient. It's a true fact that the circle is the shape which has the most area with respect to its own perimeter. This is something that they care about a lot that matters a lot in biology. They talk about surface area to volume ratio, which is a 3-dimensional thing. In the case of 2 dimensions, it would be perimeter to area ratio, which is what the isoperimetric quotient measures. So a circle has isoperimetric quotient equal to 1, and this is regarded as the best in terms of how weird the shape is. In terms of the isoperimetric quotient, the circle is regarded as like the ideal shape, the best possible shape, least weird shape. Other shapes, any other shape, are less than 1, and close to 0 is worst. Actually, it's not technically possible to have the isoperimetric quotient equal to 0. That would require the area actually equals 0. But they can be quite close to 0, and the closer you get to 0, the worse the shape is. It's the same, exactly the same idea behind the convex hull ratio, where close to 1 means a good shape, close to 0 means a bad shape. All right? This isoperimetric quotient has actually been used in the real world. It's been referred to in a bunch of court cases about gerrymandering when, like I said before, if somebody thinks that a gerrymandered district is unfair, the only recourse that you have in terms of getting somebody to redraw unfair lines is you have to take it to the courts. And so there have been several legal cases involving gerrymanders where they have actually referred to the isoperimetric quotient. Now, in American politics, they don't use this word isoperimetric quotient. So in U.S. politics, this is often the case. In the political realm, they don't use the same terminology. It means the same thing. But in U.S. politics, the isoperimetric quotient is called, it has a snappy name with somebody's name. The Paulsby-Popper score. The Paulsby-Popper. These are two people's names. The Paulsby-Popper score. As far as I'm aware, this was first used in American politics in like the 1990s or the late 1900s. So this is, as far as in American politics, a fairly new thing. Although this isoperimetric quotient has been studied by mathematicians for other reasons for a long time, and it's been used in other sciences. Apparently, I looked this up, this was first used by paleontologists digging for their dinosaur bones. Paleontologists, apparently, they care a lot about soil. I mean, a lot of different scientists do, but there was some paleontologist who wrote a journal article about specifically how about the roundness of grains of sand, like how round particular patches of gravel are. Apparently, like different, the soil in different climates have different properties, of course. And one of the things that you can study about properties of the soil is the shape, how round versus how like flat or wiggly the grains of sand are. So this was first used, I looked this up, in there was a paper in 1927 about this, specifically about how roundness of sand grains. Pretty weird, but everybody wants to use math in their own way. Anyway, the Paulsby popper, it has been used in American politics, and let me tell you, as far as I said, something which has the isoperimetric quotient close to 1 is regarded as good, close to 0 is bad. What is a typical value? So I looked up the numbers on this. For United States House of Representatives districts, our Congress districts, in the United States, which there are something like 500 something of these, 400? I don't know. There's a lot of them. Several from each state, right? For the U.S. House districts, the average isoparametric quotient right now is 0.23. All right, so this is a figure which you should regard as a typical district in the United States has a wiggliness of this much. All right, remember 1 is the best, the least wiggly. 0 is the theoretical worst. 0.23 is an average figure in the United States. The worst district, the worst in the USA in terms of the United States Congress, is Maryland District number 4, and I actually showed you this in class a couple weeks ago. I'll show it to you again. District number 4, sorry, it's District number 2. Maryland has lots of crazy districts which are extremely wiggly, like very narrow and super wiggly. Maryland District number 2 looks like this. This is the worst one currently existing, and this one has isoparametric quotient equals 0.02. That's very, very small, very close to 0, indicating super bad in terms of wiggliness, ultra wiggly. All right. I want to do some examples, like specific examples that I want you guys to be able to compute with. What makes this hard? So remember, the formula is 4 pi a over p squared, right? What makes this difficult is that the a and the p are actually in a real situation. Area and perimeter are not easy to compute, right? Area, I'm sure you know how to find the area like of a rectangle, or I'm sure you learned how to find the area of a triangle. I don't know if you remember the formula. There are formulas for these things. But how do you find the area of a weird wormy shape? Do you remember the formula for the area of a weird wormy shape? No, you don't. There's no such formula for that. There are other methods that are quite a bit more complicated. Actually, I don't know if you're aware, but one of the major applications of calculus is to find the area of weird wiggly shapes. So this A you can, in some examples, find using calculus. In the real world, they do this using computers, and it's not so difficult. If you have, say, a map of a bunch of districts, you can scan the map into a computer and compute the area without too much trouble. For our purposes, though, we are going to do this on grids. Like many of the gerrymandering examples we've looked at, we're going to look at it on grids. And then how do you find the area and the perimeter? Well, on a grid, the area, to get the area, you just count the number of squares, right? Our grids are all made up of, squares in a grid. And if you want to know the area, that would just be how many squares are inside the region. So that's easy enough. The perimeter, for that, you count the distance around the outer edge. So you count the distance around the edge. For example, if I had a grid-like shape, let's say I have a shape like this, which is made up of, a bunch of squares in some arrangement. Can we compute the area and the perimeter? Yes, we can. What's the area of this in terms of squares? You just count up how many squares there are. I got 1, 2, 3, 4, 5, 6, 7, 8, 15, right? Just like we did this last time with the convex hull thing. What about the perimeter? This we did not do last time. The perimeter, I measure the distance around the outer edge, which is like this, right? And that you can also do just by counting. You're counting a different thing. You're counting sides of squares. So when I count them, I'll do like this. 1, 2, 3, 4, 5, 6. So you got to go around the corners here. That was 6, 7, 8, around the corners here. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 I got for the perimeter. You got to count around the edge. All right. So in this example, what's the isoperimetric quotient? It would be 4 pi times area, which is 15, divided by the perimeter squared, which is 26 squared. All right. If you were doing this on a test or something, I would expect you to just leave your answer like that. If you have a calculator handy, you can plug all those numbers into the calculator. You should get a value which is between 0 and 1, right? If you get something that's not between 0 and 1, it means you screwed it up. I don't really care what the value is. All right. I got another handout. I hope that you printed out this other handout. Let's try and do some on there. All right, let's look at this handout again. This time I want to find the isoperimetric quotient of each of these shapes. I think you will find that the isoperimetric quotient is actually quite a bit easier to do than the convex hull score, because you don't really have to draw anything and you don't have to, well, you still have to count stuff up. That's all though. It's really only counting. Let's see what we can do. On the first one here, remember the formula for the isoperimetric quotient? 4 pi a divided by p squared. We got to find the a and the p squared. So the a, in this case, the area would be, I just count up the area of the boxes. It's like this. 1, 2, 3, 4. Bigot. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right, that's the area. What about the perimeter? You got to count all your way as you go around this shape. Maybe I'll start, say, right here, and I'm going to go around the shape that way, that direction. And as we go, we just count up the total distance around the edge. Watch me now as I count the perimeter. So I'm going to just mark off each little edge one at a time. I go 1, 2, 3. So I'm going up the shape this way, and then I got to turn the corner like this, right? I go count 4, and then I got to turn down 5, and now I'm going to go across here 6. Going up, see I'm going this way, right? All the way around the edge like that. So I lost count now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see what I'm doing here? Keep going. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 is what I got. You got to snake your way around the outside of edge of that shape. I got 36. And so the isoperimetric quotient in this example is 4 pi times 23 divided by 36 squared. And if you're doing this in class on a quiz or something, I would expect you to just leave the answer like that. If you really want to know what that answer is, you can type all of that business into your calculator, and I did this just for the sake of, seeing what the answer is. I got 0.22, etc. All right? So that's the isoperimetric quotient of that one, 0.22. All right, I want you to try and see if you can do the rest of them. Make sure you count up that perimeter the right way. You got to snake around the outer edge. See what you think. I'll give you a moment. All right, did you figure them out? I hope that you did. Here's how I did them. This one, first let's count the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here the isoperimetric quotient will be, it's always 4 pi a over p squared, right? In this case, I just counted a is 13. And now I'm going to go around the outer edge of this shape and count up the perimeter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. 4 pi times 13 divided by 20 squared. And that's your answer. You can leave it like that, like I said. If for purposes of comparing with the other one, if you want to see what the numbers are, I typed them into my calculator. I got 0.408, etc. All right. So as in terms of the isoperimetric quotient, this one that I just did, the 0.4, is a nicer shape than this one, the 0.22. Remember, closer to 1 indicates nicer shapes. Closer to 0 indicates wormier or uglier shapes. All right, let's try this one. Did you do this one? I hope you did this one. Counting the area first. 1, 2, 3, 4, 5, 6, 7. So here the IQ is 4 pi times 7 divided by the perimeter. Count it around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you square it. This on my calculator is 0.343. All right, something interesting about this one, if you recall from last time, we did the same example. The convex hull score of this is 1, indicating like perfectly nice shape. 1. The isoperimetric quotient is much lower than 1 in this example. Why are they so different? It's just because the two concepts are different concepts and they measure different things, you know? Let's try this one. I hope you got this one. When I do this one, I get, as usual, 4 pi times the area. All right, what's the area? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 4 pi times 11 divided by the perimeter squared. I count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 24 squared. On my calculator, that equals 0.239, etc. All right, I hope you got that. 2 more. We're almost done here. I start off counting the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is the area. Divided by the perimeter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I square it. On my calculator, I get 0.439, etc. I hope that's what you got. And finally, this one. This is a weird looking one. Doesn't really matter much, though. The area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 times 4 pi. Don't forget your 4 pi, right? 4 pi times 21 divided by, and the perimeter. Let's start here. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 32. And I got to square it. Put that in my calculator. I get 0.257 and so on. All right. I hope you got all those answers. There's not much to it. Maybe counting up the perimeter is a little tricky. You just got to get the hang of it. All right. I think that'll do it. This is the isoperimetric quotient, the other way of measuring gerrymandering geometrically. Actually, that's all we're going to say about gerrymandering, I think. Next time we're going to start something completely different. All right. Good night.